So this is lesson Unit 2, Lesson 4. Unit 2 is called Derivatives. Lesson 4 is called Differentiability. What we're going to learn in this lesson is we're going to connect our definition of continuity with derivatives. We're going to talk about when do derivatives not exist and what does it mean for a function to be differentiable at a point. So when we look at is a function differentiable at a point, it means that we can find the derivative of the function at that point and that it exists. And so a function f of x is differentiable at some value x equals a if the limit as x approaches a from the left is equal to the limit as x approaches a from the right, which is similar to our definition for continuity, although this time we're using our function is our derivative function notation. So does the derivative from the left equal the derivative of the right? So is the slope from the left equal to the slope from the right? One good thing to keep in mind as we go through this is the phrase differentiability implies continuity. And so an example of that, if a function is continuous and differentiable, and we'll look at one where it's continuous but not differentiable. So this example, g of x equals x squared, is a function that is continuous and it is differentiable. So it's continuous. X squared is a polynomial. It's a parabola. We know parabolas are continuous. And then differentiable, and this might sound silly, but if we look at the limit as x approaches -1 from the left of x squared, we can direct substitute and see that, well, it's going to approach 1. And if we look at the limit as x approaches -1 from the right of x squared, we're going to do direct substitution, and yes, you're right, just like we found before, it's equal to 1. So differentiability implies continuity was the phrase, but just because something is continuous doesn't mean it's always going to be differentiable. So here's an example of a function that is continuous but not differentiable at a point. So f of x equals the absolute value of x. It's differentiable. Is it differentiable at x equals 0? The answer is no, it's not. Graphically, we can see that, remember that absolute value function makes a v, has a sharp point at a vertex, and then changes direction. Or you could say it's chunks of two different lines that are spliced together. And so this absolute value function is continuous at x equals 0. We can draw that line without lifting our pencil. However, it is not differentiable. So if you think of our absolute value written as a piecewise function, on the left side we have the graph of a line -x. On the right side we have a graph of a line y equals x. And so we get x when x is greater than or equal to 0, -x when we're less than 0. If you do the limit of the left side, that would be the bottom one. So as h approaches 0, let's see here, we get, well, f of x equals 0. As h approaches x from the right, we get f of x equals 0. So this is our definition. We are continuous at x equals 0. Oh, and also to be really technical with our definition of continuity, we have to also make sure that f of 0 is in fact equal to 0. And yes, the absolute value of 0 is 0. So this works. It's continuous. So if we look at our definition for derivatives, we have as h approaches 0 from the left, we'd be doing, we basically be plugging in our -x into our functions. We have negative x plus h minus minus negative x over h. We can simplify this thing by distributing that negative sign. We see that the negative x and the plus x cancels out. We're left with negative h over h, which is -1. Now if we go from the right and find what would be the derivative of this function as h approaches 0 from the right, we'd be using the x function, the top one. And so we'd have positive x plus h minus positive x, which would be x plus h minus x. When the x cancels out this time, we're left with positive h over h, which is positive 1. And as you can see, the limit from the left is not equal to the limit from the right. So since the derivative from the left and the derivative from the right aren't equal, this thing is not differentiable at x equals 0. So continuous, not differentiable. Okay, so here's another kind of a, one of the extreme examples, but here's one that is continuous, but it's not differentiable. So this graph of the square root of x starts at the origin and moves upward and to the right. So this one fails the definition of continuity at x equals 0 because technically the definition is as x approaches 0 from the left, well, this has to be equal to when x approaches 0 from the right. And if we're thinking of our intervals of, or our domain at least, of this function, our domain is from 0 to infinity. And so if our domain is from 0 to infinity of this function, we cannot approach 0 from the left because there are no numbers to the left of 0 that are in our domain for this function j of x. And so technically the limit as x approaches 0 from the left of j of x does not exist. Since it does not exist, it's not continuous at this point. There's got to be at least something to the left of it on our graph. Since it's not continuous, then it cannot be differentiable. So that one's that. All right, so here is a graph of a function f. We want to find when is this function not differentiable. So from -9 to 9 inclusive, -9 would be an endpoint, 9 would be an endpoint, so those would be not differentiable because we couldn't go from the left to the right for each of those. Any asymptote, so -4, we have asymptote, so not differentiable. At x equals 1, we've got jump discontinuity, so not continuous, therefore it's not differentiable. X equals 3, we have removable discontinuity, but as it is discontinuous, so since it's discontinuous, then it's not differentiable. So we also have all of those values. Okay, so -9, -4, 1, 3, and 9 are our points where we are not differentiable for this given interval for this function. Okay, this one's a little more interesting. So from -9 to 9, notice our interval 9 is not included in the interval. It goes up to 9 but not include 9. So that means we don't have to state 9 as being not differentiable because it's not in our interval. We have less than or equal to, or -9 is less than or equal to x, so we do have to include -9, just not +9. Jump discontinuity at -6, so that's not differentiable. So now -3, here's a graphical example of what I was trying to explain earlier, of when a function could be continuous but not differentiable. And so if that made no sense earlier, try this out. So if we could tell this is continuous, we can draw this at x equals -3 without lifting our pencil, but my derivative, or my slope of the tangent line of this function as we approach -3 from the left would be, well, a line like this, it's kind of got a negative slope. And if we approach -3 from the right, we'd have a tangent line like this that would have a positive slope. Well, if the left has a negative slope and the right has a positive slope, there's no way the derivative from the left can equal the derivative from the right. So we say this is not differentiable. Continuous, but not differentiable. So -3 would be a point that's not differentiable. It's really easy to find a point that's continuous but not differentiable on a graph of a function. It would just be represented by a sharp point. We have a sharp point over here at x equals 7, so that would also be not differentiable. We have discontinuity at 4, so that would be 4 would be not differentiable. One more interesting one for this graph. So x equals negative, or x equals +1 would be not differentiable. The reason being is because if you try doing the derivative of a vertical line, well, imagine the tangent line would be just a straight vertical line. If for some reason like this actually goes vertical for just a brief moment, we would have a vertical line. Slope of a vertical line would be infinity, or not exist, in other words. And so remember from our last unit that if we have a a slope of infinity, or as a limit approaches infinity, that means basically the limit doesn't exist. Since the limit doesn't exist, that makes it not differentiable. So vertical lines is something we'll add to our list of things that aren't differentiable. Discontinuities, sharp points, and vertical lines. Those are the three things we're looking for. All right, so takeaways. We now have a definition for differentiability. It's very similar to a definition for continuity, and for good reason, because those two terms are they're not quite the same thing, but they are related. And so, as a refresher, continuity means the limit as x approaches from the left is equal to the limit as x approaches right, which is equal to f evaluated at that specific value, a. Continuity means the limit as x approaches 0 from the left of our difference quotient is equal to the limit as x approaches that value from the right of our difference quotient. And just because a function is continuous at some value doesn't mean it's differentiable at that value. Also, we kind of are also still continuing to build on our definition of derivative here using this limit function.